So, guys, welcome in. Welcome in to day 4 of AIX data. Or road to AIX data, actually. Um, my name is Soroush, your host today. I am the tech lead here in AI Club, and I am gonna talk about vision models today for you guys. It is a very, 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 very exciting topic. So, let me see if this. Okay, so. Sean, do you think we should wait a couple more minutes or should we start?
Um, Completely up to you. I have
Yeah.
no preference.
Okay. All right. We'll start. The ones who are gonna be late, they missed it. So thank you, Mindy. Thank you, William, for being here. All right. So, first thing we want to talk about is what is computer vision, in the first place. As the name suggests, is what a computer sees and then processes. And we have many, many different use cases for this. For example, there are many security features where they use object detection or they use facial recognition. Those are all vision. Um, for example, your Apple ID on your phone is a combination of vision and also some depth mapping as to like detect where every point in your face is, but the vision capturing your face and how it looks is part of it as well. So for today, we're going to go over a pretty cool data set, actually. And we're going to use classification to create a model that um, you could detect, like if you give it a t-shirt, it will know what a t-shirt, what's the difference between a t-shirt and a blouse or a dress and a pair of shoes. For this, we are going to use a data set called Fashion MNIST, which is a collection of 70,000 grayscale images for clothing. Now, um, what well, you may be asking, Suresh, why are we using a grayscale data set? Like, does that really matter? And to answer your question, I'll tell you this. It depends on what you are going to use it with. Usually, if the color is a important factor in what you are detecting, for example, if you are trying to see the difference between an apple and an orange, then yes, definitely color does matter. So you would um, need to make sure you have that in your data set, or if your data set already has it, make sure that you set your properties in a way that you use those colors. On the other side, for example, if you're trying to classify differences between a shoe and a dress, I don't think color matters. The shapes are different, right? So that is the main um, reason we're using a grayscale. And we are going to build together a convolutional neural network, or CNN for short, which is going to help us through this process. Before I continue further, there is a graph on the screen, and I want to ask you guys, is anybody familiar with CNNs in general? Do you guys know what a CNN is and how it works? No chat. The open chat. Not really, a little kinda like surface level. Okay, awesome. So this is gonna be fun. Let me cook. All right, so convolutional neural networks are I'm gonna zoom in on this as well. So we have a better view on it. Okay, so on a typical convolutional neural network, what we have is we input an image. We just give it an image, and that image goes through multiple steps in order for us to be able to create a network to detect stuff. Now, to explain this more thorough, what you do is inside of let me see if I can draw actually. Hold on. I do have my tablet slash second monitor today, so if I could do this, it will be awesome. Can you guys see my screen clearly or no?
Yeah.
Is it okay? So because I have a move this window away from shared application, it's just a zoom there. Okay. All right. So let's see this in more detail. So hear me out. When you give out an image, first thing you will do with this, you break it down into a grid, or the computer breaks it down into a grid. We already have something like that in every picture, in every screen, in every video. We call them pixels. So you are going to break down each image that you get into smaller segments that we call kernel. And each of these kernels are going to go through a few steps. Now, the first step, which is called convolution, what it does is it's a layer that separates or let me put it this way. It's a layer that performs a dot product between two matrices, where one of the matrices is a set of learnable parameters, and the other one, which is our matrix, and then the other one, oh, sorry, which is our kernel. So kernel is a matrix of learnable um, parameters, and the other matrix is the restricted portion of that field, or of that tiny little square that we have. I am not going to get too technical with the math behind it because it does have a few formulas, but each of these kernels will go into a convolution and get split into multiple ones. So if I can show you this better, convolutional network, let's see. Okay, is this good? That's not the best. Yeah, we'll go with this one. I guess we'll go with this one. So hear me out. What will happen is after you select a portion of your image, what's going to happen is you have to look into a little bit of it. So we're going to look into each of these kernels. Well, we're going to look into each of these kernels separately. In each of these, we're going to break them down again into smaller sections. Each of these sections are going to go through a process called pooling. So after we detect the matrix and see if there is anything learnable about that kernel, we're going to move over to pooling. What that does is going to allow you to run another process on it. So the other process is, I might actually need to number this. So let me see how you guys see this. Okay, so um, let's say this part will get into a matrix. I'm gonna exactly draw a matrix, and this is not the best representation. I'm not the best at drawing, but it is quite similar. So this is what we call a single depth slice. And this single depth slice will have some numbers in each of it. So just like a matrix, for example, you'll have a 6 here, a 4, a 3, a 2, a 3, a 4, 7, 9, 6, 2, 3, and then 1. And if we think of this as an X and Y as a grid, this single depth is going to again get smaller. So this gets smaller into a, for example, let's say into a 2 by 2 grid. And then we study what this is a 3, this is a 4, 4, and then 3. And then we will work with this one by putting filters and going over multiple different feature mappings. So the process is what? Convolution, pooling. We convolute again, and then we pool again until we get into a bunch of. Is it okay if I erase some of this? Guys, you guys good with that?
Yeah.
Yeah, okay. So after we're done with this, we're gonna get into a flattened layers. These flat layers will help us create different nodes, different probabilities that will later become a neural network. Why do they call it a neural network? Because it is connected in multiple ways. It is connected in multiple with multiple probabilities into multiple different nodes. And there are many, many factors in each of them um, to reach. So, for example, just like a human's body, a neuron will not just connect to one thing and that's it, done, we're good. No, it will connect into a chain, into multiple different things, multiple different neurons again, to transmit a message per se. Now, any questions so far? Okay, so after we extract all of the features, we will get to the flatten layers, as I mentioned before, and then we use each of these nodes to classify what we are actually looking for. And once we have this out of the way, we go to decide, what are we looking at? What is the image actually? Now, for you guys who said you have little experience or surface level understanding of convolutional neural networks, is this better? Do you guys have any questions? So, all right, moving on. So, let's get to creating now. All right, so we have this open. Okay, all right. So for this thing, we're going to use TensorFlow. And the reason we're using TensorFlow is because of the ease of installation compared to, for example, PyTorch, and also for the accessibility of data sets. So there's more that you guys can experiment with on this one. Um, so let's get started with it. So import, what was the first thing? TensorFlow, I guess. TensorFlow as TF, from TensorFlow dot keras. Oh, import. Let's see, we will do layers and models. We will import NumPy. And import matplotlib. Okay, so now, did anybody join me for the unsupervised um, workshop that we had a couple of days ago? If you did, you will kind of know what am I going to do right now to load the data set. So wait a second. Here we go. Did I close it? Did I close it? Oh, here. All right. So this is very, very similar in what we did on supervised training, and I'll explain how if you guys weren't there. And we'll do X test and Y test in here. Equals TensorFlow dot keras dot datasets dot fashion. Did I fashion? MNIST dot load data. Okay, so um, excuse me. Okay, so here we are loading a data set and splitting it down into two sections, a train section and a testing section. So we are going to train a model first with a part of our data set, and then we're going to test that model with those, for example, a 10% increment of it, 10% of the data set to see how it performs and use that testing to make the model a little more accurate. So after we get the X train, Y train, X test, and Y test, those are just positions. Well, points. Let's put them. Let's have them as points or vertices. So let's pre-process them. Let's make them a little bit different. So I'm gonna say. Did you want to say something, Sean?
Oh yeah, I was gonna say, I think someone asked you something in the chat.
Oh, let's see. Oh, what do X and Y represent? They are the same vertices that we talked about inside of the matrices in the kernels. You will see how they come into play in a second. So, for example, what we are going to do here is I'm going to do X train divided by 255 and X test equals X test divided by 255. Okay. Before I say anything, I want you guys to tell me what is that 255? Give it a second. I will look in the chat shortly. Four bytes, hex. Not bad, not bad. Sean, any guesses?
Actually, unironically, kind of forget. Isn't it like how you flatten the images? You have to do by 255 because of the amount of pixels or something? I'm not too sure.
Okay, not a bad guess. Not a bad guess. Let me. Do we draw? Do we draw? We'll draw. Let's draw. Okay, the reason we're using 255 there is to normalize pixel values. So is not incorrect. Hex is a good guess. Um, and 4 bytes is also a good guess because I see where you guys are coming from with those. The reason we're using 255 is because each of these values are going to give out a number between 0 and 255. So we're trying to convert this into a number between 0 and 1. Do we need to? Yes. Why do we need that? So technically it's a scale, so who cares? Who cares? The scale is from 0 to 255 or 0 to 1. Why would it output 0 to 255? That is a great question. So I actually forgot the reason it outputs 255. So let's look that up, shall we?
I think it has to do with like the RGB value, like 0 to
Is
255.
it?
Yeah.
Is it?
And then each thing inside of it like represents like a pixel and then what color the pixel is. And then like there's actually like three for red, green, and blue or something.
That is correct. So if we wanted to do colors, it would be 3 values. But I'm not sure. I want to make sure that is correct. So give me one moment, guys. Thanks for bringing it to my attention as well, William. Thank you so much. Hmm. So Sean is not correct. Sean is actually correct, but we don't have 3 of these. So draw the matrix again. Actually, um, done like a heat map is since we're doing grayscale, it's gonna be
Wait, sorry, Suresh. I want to point out really quickly that whenever you look down and talk, your voice goes away for some
microphone doesn't.
reason.
Okay,
Yeah.
I thought okay. So is this better?
Yeah, you sound good like this.
Okay, awesome. So let's do it this way then. As I was saying, so each of these are going to have a value representing their color, right? But their color is not a RGB value, it's not red, green, and blue, it's the black and white, it's a grayscale. So 0 to 255, 255 is complete white, and 0 is complete black. completely black, like turned off pixel, right? So we are normalizing this because later on when we are training the model takes in a normalized value, a number between 0 and 1, and not a number between 0 and 255. Does that make sense? Awesome. Thank you, William. I appreciate that. Okay, so let's continue. So, all right, so now it's time for, we did the X. Now it is time for, actually, we do have a little bit more to do with these, but let's do X train to equal X train, and then we have to do this dot 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 np dot new axis, I believe it was. Yes. And then we do X test, the same thing. So it's going to be X test dot 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 np dot new axis. So now you may be asking, what the heck is that now? Like you have a new thing. So let me explain that real quick. Um, Before, what we have inside of our matrix, or what we have inside of that X train, is a number of samples, which is kind of the color, like between 0 and 255. We have a height and a width, right? So after doing this, we're adding a value. We're adding a value to this, so that the dot 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 pretty much allows us to apply a new axis using NumPy, um, which is for precision and then flexibility later on. The effect it has is, just represents the number of channels. So for example, if you're doing a RGB, it will have a value of 3. But for example, right now, we'll have let's see, a value of, let's say we have 60,000, whatever. And then we have 28 width, 28 height. And then this will be converted into a something 28, 28, and 1, since we only have one channel of color. And you may be asking, Soroush, why is this so high? That is because of our data set. So this is what we call the batch size, the number of images that we have in there. And this data set by itself is divided into 10,000 for training and 10,000 for testing and 60,000 for training. So for that matter, we have a 60,000 batch size over here, a width of 28 and a height of 28, and then we also are going to add a channel over here, so it makes it easier for us to work with it. Same thing happens on X test. Any questions on this? No? Okay. So let's get the class names now. Class names equals, let's see, we have t-shirts or t-shirt. We have uh trouser. We have Go over. We have dress. We have uh, ankle boot, isn't it? Yes. Okay, so let's do coat first. Coat. We'll do sandal. Let's see. Let's do shirt. Let's do sneaker. Let's do bag. And let's do ankle boot. Now, ankle boot is quite a weird name. It's just like high top sneakers. I've never heard that term. That might be actually like a actual thing, but I speak English as a second language. I might not know what an ankle boot is. Is it a real thing or they actually name it weirdly?
I think it's real. Ankle boot.
Is it?
Yeah, it is weird though. I agree.
Let's see. Let's see if we have ankle boot. Ankle boot. Oh yeah, they call these ankle boots. Fair, fair. So mid boots. Okay. All right, all right, all right. Okay, so let's now use Matplotlib to draw some stuff. So PLT, the figure, we're gonna do a fig size of, what was it? Let's do 10 and 5. Does the size of this matter? Not really. It really depends on how you want to show it. And I'm gonna say for I in range of 10, since range of 10, since we've done 10 right there. We'll do a PLT dot subplot. Let's do 2, 5 plus I. Um, let's see, do I do 5 and then 1 plus I? Yeah. And then PLT dot show X train. We'll give it I. This guy, and 0. CMap equals great. Okay, can anybody tell me what I'm showing right here?
Uh, like the images, the tr some of the training images, but then like
Correct.
it maybe it's
Go ahead.
specific ones.
Maybe specific ones. What specific ones?
Like one from each category, maybe.
Sort of. So technically, yes. So the colon in grayscaled images from training set. Correct. That's the full answer. Yes. So the 0 means we are going to select first and only channel from the channel dimension. So if you have multiple channels, you would have to put more channels, but we only have one. So the 0 is for that. Because indexing starts from 0. And then the colons pretty much takes all of the rows and all of the columns in the dimensions of a image, and that's it. So that is the only reason we're doing that part. Just good to know how it works. And then let's see, PLT dot title. Why not? We'll give it a title as well. We'll do class names. And here we'll do Y train at 1. PLT dot axis. We will put this as off. And PLT dot show. Let's see if I did this correctly, hopefully. Any errors at all? Usually have a few of these. Yay, we do have errors. What are they? Gray is not gray, it's this, isn't it? Yep, let's try this again. Okay, now we have a boot here. And I misspelled title as well. And there we go. Okay, so what do we got? Oh, whoa, whoa, why is everything t-shirt? Oh, because I put 1. This is I. Okay. All right, here we go. Bingo. Okay, ankle boot, t-shirt. This is t-shirt again for some reason. Hmm, weird. Dress, t-shirt again. Pullover, sneaker, pullover again. Oh, because these are t-shirts, my bro. Sandal and then sandal. Okay. So now that we have these, we can get started by building our actual CNN now. So I'm gonna actually put this up here. So we have that up here, and then let's try to build a CNN real quick. So CNNs are sequential models. What that means is it goes through iterations multiple times, and it does things in a sequential manner. It goes layer by layer, as we mentioned before. So for that matter, we're going to say, we're going to define our model as a models dot sequential, and we're going to give it some parameters now. So what are the parameters? Layers dot conv 2D parentheses, and then let's give it some parameters. I'll explain these when we're there. So 32, and we'll do, let's do 3 and 3. Activation is going to be through ReLU. Input shape is 2828, and then 1 for the chat. And then comma. Layers dot pooling, or was it max pooling 2D, I think was. And then here we'll give it 2 and 2. So 2 by 2 grid pretty much. And layers dot conv 2D again. And let's do 64 here. We'll give it the 2 and 2, or 3 and 3 actually. 3 and 3 here again, and same thing again. Activation equals reload. I'll do this one and I'll explain what the heck's going on, and then I'll continue with the rest of the parameters. So layers dot max pooling 2D. Again, 2 and 2. Calm. Okay. So all right. So conv 2D, hold on. Let me go from here first. So what am I giving as a parameter to sequential model? I'm giving a list. This list is what? Firstly, I'm giving it a 2D convolution layer. After I create this convolution layer, I'm telling it that, okay, the next one is a max pooling. It's a pooling layer, which is going to get a 2 by 2 layer per se. And then we feed that into another convolution layer again, and then another pooling. But what are the parameters on each of them? So, for example, the 32 up here in the convolution and then the 64 down here is the number of filters or the kernels that we mentioned in the beginning that you detect, that you are wanted to detect from different aspects of the image. So you're trying to look for 32 parameters that might be different, or 32 things to know about that image in that grid. The 3 by 3 is the size of the grid, the 3 by 3. And the activation is ReLU. And what is ReLU? ReLU, how do I explain ReLU? Okay, so ReLU is shortened for rectified linear unit. And it's an activation function that helps helps introducing non-linearity. Is that a word? Non-linearity? Um, and help the network learn more complex patterns. And the way it does that is by zeroing out all of the negative values. That's it. So all of that talk just to say that it will make all of the negatives a zero. You may be asking, Soroush, wouldn't that make it less accurate? I will say depends on where you're using it. If you're using a grayscale image, then no, not really. If you have a negative number, then something's wrong. Zero is the max, so you don't have any color, anything higher than black. Like black is zero, flat zero. So hope that explains it well. And then we have an input shape. Can anybody tell me what the input shape is? Not Sean. Sean doesn't count. Sorry, Sean.
Boo.
20, yes, the 28, 28, 1. What are those? Close. You got two of them right. Height, width, and the channel. We don't have that. It's a 2D map. It's an image. This guy is the channel, the color channel. Does that make sense? Questions, issues, comments? I'll assume no. Okay. So if there was RGB, it would be 3, correct. If it was RGB, it would be 3. You're giving it the shape of the input. right? Even if our pictures were like 240 by 180, you would have to put 240 by 180 and then the number of channels here. Make sense? Cool. All right. So next thing, layers dot flatten. You flatten them out. Oh, wait. Capital F. This will give us the flat, what do you call them? What did we call them? Hold on. Flat layers, yes. Okay. Thought I had something else in my head for some reason. Now layers dot dense, and what we give in here is 128 activation equals ReLU, comma, layers dot dense again, and this one is going to be 10, but the activation is going to be different. Uh-oh, what are we doing here? Soft max. That looks like a that seems like a shoe that Nike would make, or a very bad Apple product for, you know. Um, but what are they? So flatten, as we've mentioned before, um, takes our three inputs, width, height, and channel, and flattens it into one number. Um, so the output shape is going to be a number. Well, it gives us a one-dimensional vector to prepare for our densing layers. Now, I'll explain what densing layers are in a second, but how this thing works is that it will take a 5 by 5 by 64 tensor and makes it a single value between 0 and 1600. Right. Now, what does that mean? That means our tensor that is a 5 by 5 by 64. Also, before I want to put this as a side note. I know it's a lot of information, so at any time, if you guys feel like there's something that doesn't make sense, or if I go off the rails, tell me that, oh, I did not understand that. That's totally okay. I will go over it again. So, where am I getting a 5 by 5 by 64? This requires a bit of drawing again. So, hear me out. Initially, what are we putting inside of our sequential model? A 28 by 28 by 1. Can we agree? If this extracts 32 feature maps, we are going to, or if it extracts 32 features or goes through 32 filters, we are going to get a 26 by 26 by, what was the value? 32. Then this guy gets fed into our best buddy pooling, and that would be a 13 by 13 by 32. Then this will go into a 5 by 5 by 64. And then this will go to a 1600 vector. What the heck just happened, Soroush? Bro, what are these numbers coming from? So if you look at the code we wrote over here, what is the size of our convolutional layer down here? We're giving a 3 by 3 filter size, right? So the way this guy is going to work, it's a little bit of map. It's a little bit of math. So let's say we do 20, wait, not drawing. Okay. We do 28. We're doing 28, 28, and then times 1. This is going to be 28 minus 3 minus 1. And this is going to give us a whopping 26. So why are we doing that? Because the way this number works, let me erase this and write it again. The way this number works is there's a formula for this. So we have the output to be input minus filter size minus 1. So we have 28 minus 3 minus 1 to be our output width or height. Does that make sense? Do we have any questions on that? Okay, I'm assuming we're all good. So after this, what we're going to have is the channels. 32 replaces the channel. Where is it? So let me see if I have a highlighter on here. Or I'll just change the color. So we have a 32 here because we have 32 filters for each of the channels. So it is now 32. Then when we run it into a max pooling or a pooling layer, what happens is this guy in a pooling, your output is going to be input divided by pool size. On a lower bound. Okay. And then this continues going on. So after we do this, we get 13, 13, 32. And then after we do this, we run another convolution layer. So that will, again, do this formula. And then we will just simply calculate this number. 5 times 5 is 25 times 64 is 1600. Questions? This is a very tough topic. It took me a second to make sure I don't mess up anything. So if there's any questions, hit me. Now's the right time. No, we are good. Okay. Okay, after this, what is dancing? Not dancing, densing. What is dense? So What dense does, it combines the features of the convolutional layers and makes it into a high level decision, right? So for the number of neurons that you will have, uh, it would be one of these created, and then they will get connected through a ReLU for the first one, and then the second one, it just makes sure um there are 10 classes because we have 10 classes from what I remember. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. So we have 10 classes, and then softmax is just going to ensure you have a value between 0 and 1 again. So now that we're out of that, next part for us is to actually compile the model. So this might give us an error, so I'm just going to delete it. Yes. Okay. So let's do model.compile. And inside of here, we're going to give it a optimizer. It does exactly what it says. It just optimizes. And they have an optimizer called Atom. There is multiple, but Atom usually works pretty nicely. So I'm not going to touch that. Let's see. This is loss sparse cate categorial uh cross I have to cross entropy. I have to check this because I am not the best with dictation. Entropy, cross entropy. Yes, correct. Okay. And last one, metrics, accuracy. Simple, easy. Now, history. I'll explain what the parameters are after I'm done with this. Just trying to save time for you guys. Fit. We're gonna give it X train, Y train. Let's give it epochs of 5 and validation data equals X test and Y test. Okay. And then we evaluate test loss. We'll do both together and test accuracy to equal model.evaluate X test and Y test. Then we print the test, test loss and the test accuracy. Whoa. I knew I will misspell this. I knew it. Wait a sec. I'm just gonna copy and paste it because there we go. What do see? Category call. Okay, there we go. That should do it, I guess. And now we wait for it to train. So till it does that, let's explain what is going on. What is going on? So, um, first things first. Oh. Let me get rid of these. So you guys have I forgot you guys can't see the screen clearly. All right, so The parameters. The parameters there, first one, as I said, is an optimizer. And the reason we're using Atom is because it's a decent optimizer inside of TensorFlow and Keras. It gives us a good default setting, makes sure everything runs smoothly, everything's good with it. And then what is the loss? Loss is it measures the error between models prediction and the true labels. And what we have over here, the sparse categorical cross-entropy, cross-entropy. How, I don't know how it's spelled, how is it pronounced either. Sparse, it pretty much means the labels X train and Y train and Y test are integers between 0 and 9. So we're converting everything into integers and not one hot encoded vector of like 0, 0, 1, 1, 0. And that's pretty much it. The metrics that we're trying to measure is the accuracy, and that's it on that. And after we go above here, we just fit the model, we give it our training data, we give it the amount of epochs. Does anybody know what epoch is and how it works? Mindy, no. Okay, so epoch means the number of training iterations that you go over the entire data set. So what it does is, for example, if you process your 60,000 data points inside the data set 5 times, you will process it 5 times, and every time it will update the weights on the epoch. So it's like you do something again and again and again and again to make sure you understand it well. But instead of you, the AI is doing it, right? It's like you're memorizing something, but you want it to um, you have to read it a few times in order for you to be able to do that. Now, here we have our results. So this is the training loss, and this is our training accuracy. 0.9 is 90%. That is not bad at all. So I wonder if I raise the epochs, will this be a bigger number? What do you guys think?
Maybe.
Maybe. Okay. So I am going to raise this to 10, so double what we have, and move over to the next section so that while this guy does its thing, we finish up the code. Jason says, yes, I do. What was that for? Oh, that was for the epoch. Sorry, my fault, my fault. Okay, so let's just make two figures down here. PLT dot, what was it? Figure. Fig size equal 12 and 4. PLT dot subplot, and we will do 1, 2, and 1. No, we're gonna do PLT dot plot history, history of our accuracy, and our label is going to be training accuracy. And then we'll do plt dot plot. Same thing actually, but difference being instead of accuracy, I'll do valuation accuracy and validation accuracy down here. Title is gonna be, let's see, plt.x label is gonna be epoch. plt.y label is gonna be accuracy. And plt.legend. Now I'll do another one, same exact thing, but then since I don't need this one actually, just do this, and instead of accuracy, I'll do loss, train loss, and then val loss, validation loss, and then model loss, epoch, and then this one is also loss. Okay, so we're almost done here with the training as well. That was decent timing. We're almost done with the training and we got done with the visualization. Now, already, guys, we can see the value or the accuracy here is 94. And then on this one that we haven't finished yet is almost 95. This one is 96 now. Whoa, what's going on? From only 5 more epochs, you can get this much of a difference? Yes and no. Again, it depends on your data set. It depends on many factors, actually. Data set is one of them and probably one of the most important ones. But usually the more amount of times that you go over the whole data set, the better it will work. Um, that is a no-brainer. It's like practice makes perfect, pretty much. But there's a limit to it because this is not a linear thing. It's not like you do like 20 epochs and then it will it will get like 50% accurate and then you do 40, it will get 100%. No, it doesn't work like that. I apologize. I wish it did, but it does not. You can see we did 5 more epochs here, right? We got from a, let's say 91.08 into a 91.09. The difference is very, very, very slim. Now, if we do 100 epochs, is it going to make a huge difference, you think?
No.
Not really. It might make some difference. It might be like 91 pause 91.5 instead of 90 point no, bro 91.0809, but it is not going to be that huge of a difference. And if I run this here, let me see, there we go. Okay, if I run this, of course, what is Soroush without some misspelling? History. History. That is crazy. Okay, here we go. History is not defined. What do you mean it's not defined? Oh, I misspelled history itself. Okay, that is awesome. His Troy, I guess, guys. His Troy. Okay, so let's see this. Let's see this. So the training accuracy was a constant almost line. You see how it is kind of exponential? It's like curving little by little upwards, but it will probably never reach one. It will probably never reach one. There's no such thing as 100% prediction. And the validation accuracy is a little bit lower than that. Hmm. Do we know what is the difference between training accuracy and validation accuracy? Basically, training accuracy is what your model thinks it's getting right based on the input and output that you gave it. And the validation accuracy is after you give it that test set of from the data set and ask it to, oh, can you do this? Can you actually like validate? Let me see how you do it. You do have the outputs already, but you want your model to predict it and compare the two. So our actual thing is, our actual output is closer to this line than it is to this one. Same thing over here. So the loss we can see is way, way, way more steep inside the training than it is in validation. To conclude, CNNs are very, very powerful. They are very fun to use, and there's a lot to learn about. I try to fit as much information in this workshop as possible. I try to make it as dense as possible. So even if you guys couldn't go through everything inside of this session, you can watch the VOD and be like, okay, I can pause it and then write something down. It might be a little useful, it might come in handy. And yeah, that would be all from my side. I would suggest looking over um, convolution neural networks a little bit more because there's a lot you can do with it. It's not only limited to this example and the way I trained the model. There's a lot more that you can do with this. And yeah, that's pretty much it. Do you guys have any questions for me? Do you think this was a helpful workshop? Awesome. I am happy to hear that. Alrighty, if you guys don't have any questions, I'll let you guys go. Enjoy your night. It's a very rainy day and a beautiful um night, actually. So yeah, good luck on everything. I'll post the links. I'll have our best vice president ever, Sean, post the links for you guys. I will put some sources beneath this as well, just like extra reading if you want to go the extra mile. And yeah, take care, guys, and I'll see you in the next one. Actually, I'll see you in Datathon. Take care, guys.